Europa Clipper is already on its way. Launched in October 2024, NASA's Europa mission is heading toward Jupiter right now, and it will arrive in 2030. Before it gets there, James Webb has already changed what we're expecting to find. This is Europa, an ocean world orbiting Jupiter 780 million kilometers from Earth. And it may be the most important destination in solar system exploration. For decades, space science treated Europa politely. A frozen moon of Jupiter. Pretty in astronomy textbooks. Mentioned in solar system documentaries, then moved past. But beneath that clean white shell, an ocean. A real one. Global. Possibly containing more liquid water than every ocean on Earth combined. And recent NASA Europa mission data has forced researchers to take the question of life on Europa seriously. No, seriously. In a way they couldn't before. Europa's ocean sits beneath kilometers of ice, orbiting Jupiter in a gravitational dance that generates enough heat to keep that water liquid for billions of years. That makes Europa an ocean world, unlike anything else we found in space exploration. A place where the basic ingredients for life on Europa may have been quietly assembling in the dark for longer than complex life has existed on Earth. What if the answer to the oldest question in astronomy, are we alone, has been sitting in the Jupiter system this entire time? Europa Clipper's mission is to find out. And what James Webb already discovered before Clipper arrives changes the calculation entirely. Here's what we know, and what it means for anyone thinking seriously about what comes next. But before we get into it, I just want to take a moment to thank every single person watching this. Your time and attention genuinely mean everything to me. Now, let's get into it. Europa is one of Jupiter's 4 Galilean moons discovered in 1610. Slightly smaller than our moon, about 3,100 kilometers across. From the outside, it looks like a cracked egg. Almost featureless white ice crossed by reddish-brown ridges that stretch for thousands of kilometers. We've suspected a subsurface ocean since the late 1990s, when NASA's Galileo spacecraft detected disruptions in Jupiter's magnetic field near Europa that could only be explained by a vast body of electrically conductive liquid below the surface. A global ocean sealed under an ice shell estimated between 10 and 30 kilometers thick. That ocean is what made Europa worth talking about. Liquid water is the one ingredient every known form of life requires. Ga. Its presence doesn't guarantee biology, but it opens the door. And for 20 years, an open door was all we had. We couldn't see through the ice. We couldn't measure what was dissolved in the water. We couldn't tell whether the chemistry down there was interesting or completely inert. We were standing outside, pressing our faces against frosted glass. What that means for survival planning. An ocean you can't access, music beneath ice you can't see through, is just a hypothesis. You can't build a mission around a hypothesis. You need data. And, until very recently, we didn't have nearly enough. James Webb didn't drill through the ice. It didn't land a probe. It did something quieter, and, given the distance involved, almost unreasonably precise. It stared at Europa's surface with the most sensitive infrared spectrograph ever built. And read the chemical signatures of what's actually there. In September 2023, two independent research teams published results from Webb's near-infrared spectrograph, an instrument capable of identifying specific molecules on a surface more than 600 million kilometers away. They were looking for carbon dioxide, not because carbon dioxide is inherently significant, because of what its presence would mean. Carbon dioxide on Europa's surface can come from two sources. It can arrive externally, carried by meteorite impacts or radiation from space, or it can come from inside, pushed upward from the ocean through cracks, mucus in the ice over geological timescales, deposited on the surface like a stain seeping through fabric. If it came from below, it would mean the ocean contains dissolved carbon. Carbon is the structural backbone of every known form of life. Both teams found it, concentrated in a region called Terra Regio, a geologically young, heavily disrupted area on Europa's trailing hemisphere, not scattered thinly across the surface. Music the way random meteorite delivery would, localized, sitting in exactly the terrain that geological models predict would be refreshed. Music by material welling up from the ocean below. Lead researcher Geronimo Villanueva at NASA's Goddard Space Flight Center. The distribution was consistent with an internal origin. The ocean contains dissolved carbon dioxide, and the geological activity at Terra Regio had brought traces of it to the surface. What that means for survival planning. Carbon in the ocean is a prerequisite for the chemistry that could support biology. It's also a prerequisite for synthetic chemistry, the kind of industrial processes a human presence, music, would eventually depend on. An ocean with dissolved carbon is more music useful than an ocean without one. Webb just confirmed Europa has it. Astrobiologists generally describe 4 conditions necessary for life to be plausible: liquid water, an energy source, the right chemistry, and sufficient time for complexity to develop. Before 2023, Europa had confirmed 2: water and energy. Webb just added a third: carbon, and Europa has had the 4th: time, for billions of years. I want to be careful about what this means and what it doesn't. Detecting carbon dioxide on a distant moon is not the same as detecting life. The distance between conditions that could support life and conditions that actually produced it is enormous. And we have exactly one data point for how life originates: Earth. Drawing broad conclusions from a sample size of 1 is poor science, regardless of how compelling the pattern looks. What Webb has done is remove one of the reasons to rule Europa out. Before these results, someone could reasonably argue the ocean might lack the dissolved carbon needed. Music for any interesting chemistry. That argument is now harder to sustain. The door hasn't opened wider, but we've confirmed it's still there. Europa is 780 million kilometers from the Sun. Solar energy at that distance is negligible. The surface sits at -160 degrees C. By every surface measurement, this moon should be frozen all the way through. The energy source isn't the sun. It's Jupiter. Europa's orbit is slightly elliptical, nudged into that shape by the gravitational competition between Jupiter and its other large moons, particularly Io and Ganymede. As Europa moves closer to and farther from Jupiter, during each orbit, the planet's gravity squeezes and stretches the moon's interior in a continuous cycle. Tidal heating, the friction of that constant deformation, generates heat sufficient to maintain a global liquid ocean beneath kilometers of ice, and has been doing so for an estimated 4 billion years. More than that, it likely drives hydrothermal activity on the ocean floor, hot vents where mineral-rich water meets cold ocean. Rocky seafloor in direct contact with liquid water, cycling chemistry upward through convection. This is the environment where life on Earth is now believed to have originated. Not at the sunlit surface, at the dark bottom of a cold ocean near vents in the rock. Europa's ocean is estimated between 60 and 150 kilometers deep. The Mariana Trench, the deepest point, music in Earth's oceans, reaches about 11 kilometers. Europa's ocean could be more than 10 times deeper, contained inside a moon smaller than ours. What that means for survival planning. The energy problem, the first thing you'd need to solve for any long-duration presence, may already be solved by Jupiter. Not solar panels, not a nuclear reactor we'd have to bring. Tidal heating is continuous, planetary in scale, and has been running for 4 billion years without interruption. For a colony that needs power indefinitely, that's a more reliable baseline than anything we could engineer. The harder problem is access. Here's where Europa becomes genuinely strange. Jupiter bombards Europa's surface with approximately 540 rem of radiation per day, enough to deliver a lethal dose to an unshielded human in roughly 4 hours. This radiation, destroys complex organic molecules on the surface within decades. Any chemistry that rises from the ocean below gets chemically dismantled before we could detect it from orbit. But that same radiation also splits water ice and other surface molecules into fragments that recombine into new compounds, including hydrogen peroxide and molecular oxygen. Some models suggest that this radiation-produced oxygen is being slowly fought back down through the ice into the ocean below, where it becomes available as a chemical energy source, fuel for any organisms that might exist there. Moon is more. Jupiter's radiation sterilizes the surface, and filtered through 30 kilometers of ice, that same radiation may be delivering oxygen to the ocean as a resource. The thing that makes the surface lethal to humans might be feeding whatever lives beneath it. Europa doesn't operate by intuitive rules. What that means for survival planning. The surface is not where humans would live. 4 hours of lethal radiation exposure is not a problem you solve with engineering optimism. You solve it by going underground or under the ice. Any serious human presence on Europa would exist within the ice shell itself, shielded by the same 30 kilometers of ice that protects the ocean from radiation above. The ice isn't just an obstacle. It's the habitat. This reframes the entire engineering challenge. The question isn't, how do we survive the surface? The question is, How deep do we need to go before the radiation budget becomes manageable? And the answer, based on current models, is not as deep as you might think. 6. When researchers examined Webb's spectral data more carefully, they found something that didn't make the main headlines, but matters considerably for anyone thinking about long-term human operations. The carbon dioxide wasn't alone. It was mixed with specific salts, sodium chloride and magnesium sulfate, table salt and Epsom salt, the same kinds of dissolved minerals found in Earth's oceans. Their presence in the same disrupted terrain, where the carbon dioxide was concentrated, suggests a connected system. Sal? Henri, the ocean communicates with the ice. The ice eventually, music, communicates with the surface, and the surface communicates with space. Webb caught that conversation in progress. The salt composition also feeds directly into habitability modeling. On Earth, hydrothermal vents produce specific mineral ratios depending on the temperature and chemistry of the surrounding rock. If Europa Clipper can measure precise salt ratios on the surface and reference them with tidal heating models, scientists will be able to estimate the temperature and chemical environment of the ocean floor without music sampling it directly. Music ever sampling it directly. What that means for survival planning. Salt is not just a chemical curiosity. Sodium and magnesium are minerals any biological or industrial chemistry requires. An ocean, with the right dissolved mineral profile, is a resource, not just a scientific curiosity. Webb just told us, Europa's ocean has a profile that looks, at the dissolved mineral level, like something familiar. NASA's Europa Clipper launched in October 2024. It carries 9 instruments, the most sophisticated suite ever sent to the outer solar system. It arrives at Jupiter in 2030 and will execute approximately 50 close flybys of Europa, some passing within 25 kilometers of the surface. It cannot orbit Europa directly. Jupiter's radiation belt would destroy its electronics within weeks, even with a titanium radiation vault nearly a centimeter thick protecting its core systems. Each flyby is a race against cumulative damage. The mission is designed around brief, precisely targeted passes, retreating to safer distances between observations. One instrument is called SUDA, the Surface Dust Analyzer. Its job is to catch and chemically analyze microscopic grains of ice and dust kicked off Europa's surface by micrometeorite impacts. Each grain is a frozen sample of whatever material sits on or just below the surface. SUDA doesn't need a dramatic eruption to get useful data. Even the faint haze of particles from routine surface impacts is enough. One grain with the right molecular signature could change the entire conversation. Clipper also carries Reason, an ice-penetrating radar designed to map the interior of the ice shell to approximately 30 kilometers depth. Theoretical models predict pockets of liquid water trapped within the ice shell itself, sandwiched between the frozen surface and the music deep ocean below. If those subsurface lakes exist, Reason should detect them as bright reflections at shallow depths. That matters enormously, because it would mean liquid water might exist at a depth that's actually reachable. Not the ocean floor at 100 kilometers, but pockets potentially music accessible at 3 or 5 kilometers of ice. Webb's carbon dioxide discovery gave Clipper a specific target, Tara Regio. Already geologically interesting, now chemically significant, is a priority observation site. Disrupted terrain, carbon signature, fresh ice, all pointing to a location where the ocean is actively communicating with the surface. Clipper's job is to listen to that communication at close-range MUGIC and decode it. What that means for survival planning. Clipper is the reconnaissance mission, everything we're discussing. The habitability questions, the resource assessment, the engineering challenges will be answered or sharpened by what Clipper returns between 2030 and 2034. You don't plan a presence at a location you haven't surveyed. Clipper is the survey. In March 2024, Webb searched for plume activity, jets of water vapor, erupting from Europa's surface into space. Hubble had reported possible plumes in 2012 and 2016, but those detections were marginal. The scientific community was divided. Webb found no large, persistent plumes during its observation window. That sounds like a setback. It tells us something useful. Saturn's small moon fires geysers continuously from its south pole. Europa appears to behave differently. Any outbursts that occur are likely intermittent, possibly triggered by specific tidal stress patterns at particular points in the orbital cycle. For survival planning, this distinction matters. A moon with continuous plumes is a moon that's actively venting ocean material into space, which means easier sampling from orbit, but also a more energetically volatile interior. A moon with intermittent plumes has a more stable system, easier to be near, harder to sample remotely. Clipper's 50 flybys are partly a probability exercise, enough passes that statistics work in favor of catching an active music event if one occurs. If you were standing on Europa's surface, which you wouldn't be, not without dying quickly, Jupiter would dominate the sky in a way that has no equivalent on Earth. Not a bright point of light, a wall. Jupiter would fill nearly 24 degrees of sky, roughly 48 times the apparent diameter of the full moon as seen from Earth, banded in oranges and browns. The great red spot drifting slowly across its face. And you would understand, immediately and physically, that Europa doesn't exist independently. It exists because Jupiter permits it to. The tidal forces keeping the ocean liquid come from Jupiter. The radiation, sterilizing the surface, comes from Jupiter. The gravitational resonance that shapes the orbit, and therefore generates the heat, comes from Jupiter's competition with the other moons. But the people who would actually live wouldn't be on the surface. They'd be inside the ice. Picture a habitat melted into the ice shell at a depth where radiation levels become manageable, perhaps 5 to 10 meters below the surface, where ice provides shielding, without requiring you to drill to the ocean. Power drawn from a reactor using the ocean's chemistry as a reference. Water extracted from the surrounding ice. Communication with Earth on a 43-minute, one-way delay at maximum Jupiter distance. The ice is the architecture. The ocean is the resource. Jupiter is the power plant. None of this is close. None of this is the next decade or the one after it. But the infrastructure of the question, what would it take? What do we need to know? What are we looking for? That's being built right now by Webb's observations and Clipper's trajectory. Here's where the survival calculus actually stands. Europa has confirmed liquid water, a long-duration energy source, dissolved carbon, salts, dissolved salts, with a familiar mineral profile, and geological activity that cycles ocean chemistry toward the surface. That's a more complete habitability picture than we had 2 years ago. What it doesn't have, a surface you can safely occupy, a gravity field that's remotely Earth-like at 0.134 g, any proximity to resupply, or an ice shell we know how to penetrate with existing technology, a round-trip communications delay that reaches 86 minutes at maximum separation, radiation that would require any surface or near-surface habitat to be heavily shielded from day one. Europa is not a comfortable destination. It may not be a destination for humans within this century, but it may be the most scientifically important location in the solar system for answering the question that precedes every other question about long-duration human expansion. Are we the only chemistry that got this far? If Clipper finds organic molecules in those ice grains, not life, just the building blocks, it tells us that the chemistry of biology is not unique to Earth. That wherever the conditions megalithic align, the universe trends in this direction, that we are not a fluke. That changes the expansion calculus in ways that are hard to overstate. We're not going to Europa because it's easy. We're watching it because it may tell us something about ourselves that no other place in the solar system can. Webb opened the question properly. Clipper is already on its way to answer it.